Okay, we are moving to our second session of the first day. So I would like to welcome Mr. Deepak Berwal, who is a research scholar in Department of Electrical Engineering, IIT Bombay. And his topic is biomedical signals, opportunities and challenges. So I'm very happy to introduce you all with him. So he has received his B.Tech and M.Tech degree from Algotias University. He is a gold medalist in M.Tech degree, and currently he is pursuing PhD, about to finish his PhD from Department of Electrical Engineering, IIT Bombay. His current research interests include signal processing and system design for biomedical applications. He has won the D.S.T and Texas Instruments India Innovation Challenge Design Contest. Many of you must have heard about this. Many of the institutes actually participate in this design challenge. So he has won this particular amount, huge amount under this contest. Now he is also the director of the startup of his company, I Smoke Solutions Private Limited. So with this brief introduction, I would like to invite Deepak Berwal sir and request him to start his session.
Thank you, Amol sir.
Yes, I will stop sharing.
Yes. So now I am sharing my screen.
Yes, please. Yes, your screen is visible. Your slide is also visible.
So can I start?
Yes, please.
Yeah. Okay. Yeah. Thank you, sir. So good afternoon to all. So I am going to present a seminar on biomedical signals, opportunities and challenges. So I am a PhD research scholar in IIT Bombay. So we start with the biomedical signals. So what is biomedical signals? So biomedical signals are observations of the physiological activities of human body, of like human organs, tissues, cardiac activities. So we will discuss in detail about these signals. So these are some outlines like how I will proceed further. So first I will start with the motivation. Why do we need these signals? Okay, then various type of human body signals, then biomedical systems, portable and wearable devices, then various type of challenges that we face during the acquisition of these signals, and then how we process these signals like artifacts, noises, then feature extraction, then various applications of these signals. And then there are some online databases available freely, and we can use these signals from these databases and process for the research purposes, and the opportunities in the biomedical field, and then references. So we all know that when a patient goes to the doctor, so doctor has to monitor this patient, okay, for particular disease or some treatment. So for this we need a signals, maybe some heart signals, some muscle signals, or some brain signals. So first we process these signals, and then based on these processings we have to take decision. So doctor will take the decision based on these signals, and then start the treatment of the patient. So based on these signals, the doctor gets to know about the patient's, the functionality of the organs and the health of the patient. So there are various type of applications, like these signals are used in the patient monitoring in the ICU, disease detection and the diagnosis, preventive health cares, human machine interface, something like the wheelchair, the prosthetic control. So we need the human machine interface for these signals, then treatments, and to understand the physiology and functionality of the human organs. So we need these signals, biomedical signals. So there are various type of body signals. biomedical signals. So we start with the upper portion of the body, like EEG signal, that is called electroencephalogram. So there are three colors in this, if you see. So first color, the red color shows the type of signal. Like electro means it is an electrical signal. Blue color shows that it is related to which organs. It is encephalon means brain, related to brain. Gram means how to represent the signal. Like gram means picture. So we are using this for the representation purposes. So EOG, electrooculogram, it is a retinal signal which we extract using some instrumentation. Respiration signal, electrocardiogram, phonocardiogram, that the heart sounds, impedance cardiography, all these are related to the heart. Electromyogram, the muscles noise, the muscle signal actually. BP, blood pressure. Electroneurogram, ENG, neural signals. Photoplethysmogram, photo means optical. Like we acquire these signals through the optical process. Impedance, like we have to measure the body impedance. So these signals are related to the human arteries and body temperature. So these are the typical biological signals which we acquire and process to observe the functionality of the human organs or tissues or for the treatment and monitoring of the patients. So to acquire these signals, we need various type of sensors. Like, so there are various type of sensors available in the market, and we can use these sensors for the research purposes also, or we can make these sensors also. So there are various type of sensors such as biopotential sensors, optical sensors, capacitive sensors, chemical sensors, resistive strain sensors, and some motion sensors for the acceleration measurements, some motion detection. So biopotential signals which measures the voltage like ECG, EEG, EMG. Optical signal which measure the the PPG signals. Capacitive sensor which measure the impedance, the bioimpedance signals. Chemical sensors, we can use these chemical sensors for the pH measurement or some sodium or ammonium in our sweat. Resistive sensors are mainly used for the pulse measurements. So this is the analog signal conditioning blocks. And for to acquire these signals, we need some power management and battery. So this is a system and sensors. So after acquiring these signals, we have to transmit these signals to the systems. Using some microcontroller, we transmit these signals to the smartphone, computer, or some particular device which are used for the display purposes. So there are various type of connections: wired connection, wireless, Bluetooth, Wi-Fi, or specific biotelemetry systems. So these are the short-range communication. So after receiving these signals at this end, then doctor can observe these signals and take the decision for the patient. So sometimes the patient is not in hospital, then what can we do? Then we have to send these signals to the doctors, like for the remote location. If the patient is in the rural areas, there the old facilities and doctor is not available, then we have to transmit these signals to the long range communication, and then doctor will take decision and will reply based on these outputs. So there are various type of biomedical systems. These are the typical portable medical devices which are used in the hospitals. Yes, upper one is the laboratory equipments which are used for the like blood testing. Okay, and then we use some microscope to see some particular disease in the blood. And there are some medical equipment such as like these display. We can see the various type of signals are displaying here. So these are portable and they are bulky actually. So these are mainly used in the hospital. But nowadays, there are some wearable devices also, wearable biomedical devices. So if you see various type of medical wearable devices are available in the market, we can use these for various type of applications, maybe for the heart rate detection, calorie burn, sleep disorder, for muscles movement detection, these glasses, strips, belts, shoes also. Okay. So these are the wearable devices which are commercially available. So, so these signals, if we see these signals, like what is their frequency range, amplitude. Okay. So EEG, the brain signals, normally has the frequency range of zero point 0.1 to 100 hertz and has the amplitude of 1 microvolt to hundreds of microvolt. So actually these signals are very low amplitude in nature. So so there are various EMG, PPG, ECG, neuro signals also. So these signals are very low amplitude and has the various band of frequency. So if you see like the respiration rate, blood pressure, body temperature, SpO2 is blood oxygen saturation level. So these are the range, typical range of these body parameters. So if we want to process these signals or these parameters, we have to make a system in such a way that it will measure these signals, amplify these signals. Okay, so these are the challenges, like how to acquire these signals and then proceed further. Okay, so I start with the various challenges with these biomedical signals. First is the hardware. Like we have to amplify these low amplitude signals in particular frequency band. So this is a challenge actually. We have to make an amplifier, very low noise, and these, because when we are making these systems like for wearable and portable applications, so the device should have the low voltage. So if the DC offsets are not removed from these signals, then the signal will saturate. So we have to first block the DC offsets. So these are some technical terms. So we have to reject some common mode noises in the signal, and we make the system low power to facilitate for the wearable and implantable applications. So these are some hardware challenges. And now for the software part. So first we reject some noises at the hardware level, but after rejecting at the hardware level, we are also getting some noises at the software level also. Then we have to remove at the using laptop or some particular device. Okay, so these noises we can remove using some simple filterings, but sometimes these noises and artifacts overlap with the signal in spectral and temporal domain. So we have to use some specific technique to remove these noises. So these are challenges. It is not simple like we can remove using some simple FIR or IR filters. And if we don't remove these noises, then it can create the false alarm or errors, which can lead to the mislead the diagnosis and treatments. Okay. So normally traditional signal processing techniques fail to process these signals. Okay. And after, if we process these signals, then after that we extract some features from the signals and then estimate some body parameters, maybe the heart rate, oxygen level, BP, body temperature. So we have to estimate these parameters, but accurately with minimum error. So these all are challenges with these biomedical signals at hardware and software levels. So I will start with these biomedical signals, various types of signals. So one by one, I will discuss some signals and we'll proceed further. So I will start with the electrocardiogram signals. This is normally called ECG signals. So ECG signal is a graphical representation of electrical activity of the heart. So this is a typical ECG signal which has the amplitude of 2 to 3 millivolt and has a range of 0.8 to 0.9 seconds. So In this, there are various peaks, P, Q, R, S, T. So these are the name of these peaks. So we use these peaks to process the signal. So this signal has this amplitude and frequency range. It has normally 0.01 to 150 hertz. It can go till 250 hertz, but typical range is 150 hertz. So to acquire these signals, we are using some AGCL electrodes. So these are the electrodes which are normally available in the markets. So this is front and back side of the electrode. Okay. So there are various type of ECG acquisition. Okay. So this, it is called one lead acquisition, in which we use 3 electrodes. RA means right arm, LA means left arm, RL means right leg. So we use these electrodes. So here RA and LA are work as a differential part of the signal. So we acquire signals from RA and LA, and using a differential amplifier, we amplify and extract the ECG signals. So right leg drive is used for the feedback purposes here, to reduce the common mode noise. Okay, so this is called 3 lead, in which we use one lead from the RA minus LA, second from the LA minus LL, that is the RA minus LL. Okay, RL is the feedback. So we don't use RL for the acquisition purposes. So this is the typical 12 leads configuration, which are mostly used in the hospitals. Okay, so there are 10 electrodes, but from these 10 electrodes, we can extract the 12 ECG signals. So this is an example of 12 lead configurations. Like this is a patient, and these are the systems which are connected to these electrodes. So if you see, there are 10 electrodes are connected, for 2 at the upper part, 2 at the lower part, and 6 in the near the heart. Okay, so these are the configurations used for the ECG acquisition. So this is a typical basic ECG acquisition circuits. If you want to know more about this, you can check this link. Okay, so when we acquire these signals, so this is a differential signals then we are acquiring. So typical circuit diagram, in which first we use a buffer for the high input gain. Okay, for the high input impedance. After that, we use the INA to amplify these signals, and then we use a programmable gain amplifier and a low pass and high pass filters to remove some particular band, out of band noises. Okay, so the lower one is the right leg drive, which is used for the feedback to remove the common mode noises from the body. And this is the bias voltage, simple voltage divider circuits. So this is a typical ECG acquisition systems. Okay, so output is the ECG signal. So when we record these signals, so we are always stay still, like there should not be any noise. But if you want to do some research, then we have to generate a noise first to remove these noises. So we can do various type of activities to record these noises. Like these are daily activities: the hand raise, bending down, sitting, walking, hand crossing. Okay, the waist movement. So using these movements, we can do the various motion artifact generations. So now I will go for the electromyogram signals. So what is electromyogram signal? Electromyogram is a graphical representation of electrical activity of the muscles. So these are the typical example of the EMG signals. So there are 2 EMG signals here. Below, in between that, there is a baseline which does not have any signal, and these are the muscle activities when we do any activity. So it has typically 0.1 to 5 millivolt range, or more than that. It typically depend on our activities. and it has a frequency range of 10 to 1000 hertz. So this EMG is also, we can record using the same ECG electrodes, like ECG electrodes, and using the same system, but we have to increase the bandwidth of the system till 1000 hertz. Okay, so if you see in this diagram, the electrode 1 and electrode 2, so we can, using these electrodes, we can acquire our lower arm muscle movements. Okay, so these are the placements, typical placements, but we can use these electrodes at anywhere in the body where we want to acquire the signal. So now we go to the another signal, electroencephalogram, that is typically called EEG signal, which is the electrical activity of the brain from the scalp. So this is a typical example how we record these EEG signals, electrode and the scalp. Okay, so there are multiple electrodes configurations using this EEG signals. Okay, and these are the some examples of EEG signals. So various type of EEG signals are there. So delta, theta, alpha, beta, and each of these signals has various frequency band and various amplitudes. And based on these signals analysis, we can process like how our brain is working, how to what we are thinking at particular point of time. So we can extract some information using these signals. So for these, there are various type of electrodes: stainless steel electrodes, tin electrodes, gold and silver electrodes. So we can use the same EEG electrodes for this EEG acquisition also. Okay. So there is another signal called photoplethysmogram signal, PPG signal. It is an optical signal which are normally used to detect the blood volume changes in the tissues. Okay, so this is the typical PPG signal which has like this shape where this peak is called the systolic peak, then dicrotic notch and diastolic peak. So we acquire this PPG signal using a light source, red and infrared signals, and we detect these signals using a photodiode. Okay, so there are two type of configurations used. One is the transmittive and one is the reflective. Okay, if you have seen this type of LED and photodiodes in the wearable watches, if you see that green lights are there in wearable or some smart watches, so they use this reflective type of configurations for these PPG signals, and then they extract the heartbeat from this signal. Okay, so this is normally used in the hospitals like PPG finger probe. So we use this in the hospitals, and this is a typical diagram of the PPG recording system. Like we have a voltage control consoles, so that will provide the current to the LED, and then based on the LED outputs light, it passes through our finger, and then using the photodiode we acquire the light, and then we amplify the signals and then convert the signal from analog to digital, and then give the output further. Okay, so now we are going to talk about the BP, blood pressure. Okay, so everyone knows about what is a blood pressure. It is the physical force exerted by the blood as it pushes against the walls of the arteries. So normally when our heart pumps, so BP is the highest when the heart contracts and falls when the heart is relaxing. Okay, so arterial BP are normally measured using a commercial sphygmomanometer, and it is considered the gold standard. Which doctor always use this device to measure the BP. Okay, so these are some typical range like 120/80. So there are always two values. One is the upper value and next is the lower value. So upper one is called systolic BP and lower one is called diastolic BP. Okay, so our value should be around these numbers or less than these numbers. If it is crossing more than these numbers, then we have some BP problem. Then we have to go to the doctor. Okay, so how the doctor measure this BP? Okay, so these are the steps how we measure the BP. In step one, we know like we have the arteries in our upper arm and lower arms. So we put a cuff. It is called cuff. So we put the cuff at the upper arm and then inflates it with the air. When we increase the pressure, it goes above 120. So after it goes above the 120, then we try to reduce the pressure using some knob, and doctor measure the sounds at this site. And when he listen the sound, when he decrease the pressure, and the blood will start when the internal pressure and the outer pressure will become equal, then the artery will start opening and blood will start flowing. And from that point, doctor measures that it is a systolic pressure, and when the sound stops, it measures as the diastolic pressure. So this is the typical BP measurements used by the doctors. So there are some devices. These are some portable devices which are normally used in the home, like home BP monitoring devices. So we can also measure by ourselves. This is a cuff, and this will automatically detect the BP values. Okay. So we have gone through various signals and their properties and how we can record these signals. So after recording these signals, we have to do some signal processing. Okay, like if I consider the ECG signal, it is a noisy ECG signal. So we have to process these signals. To process these signals, first we have to denoise these signals because it has a noise. So we cannot predict anything from these signals. So doctor never accept the noisy signals. Okay, so to process these signals, we have to do some filtering at the software part in the whole particular systems. Okay, so there are some basic filterings: FIR filtering, IIR filtering. So we can use this filtering. There are some adaptive filterings, some wavelet filterings also. Okay, so it is not easy to remove these noises because these are not out of band noises. If these are out of band noises, we can remove these noises from using IIR or FIR filters. Okay, after removing these noises, we can extract the features from these signals. Okay, time domain features, frequency domain features, some statistical features. Okay, because why do we need this feature extraction? Because after processing, how to predict or how to estimate the body parameters. Maybe one of the example is the heart rate. If we consider the heart rate, then after denoising, how to calculate that heart rate? If we detect these ECG peaks, there are two peaks are there, and then what is the timing difference between these two peaks? So consider that typical example is a 0.8 second. So what is our heart rate? So we use some formula like the 60 seconds divided by that 0.8. We will get the 72 beats per minute. So this is the example how to use these feature extraction to calculate the body parameters. Next is the body parameter estimation. So we can use some formula which are already defined in the literature, or we can derive the formula to estimate the body parameters. Or if we don't know the exact equation to estimate these body parameters, we have to use some curve fitting techniques. Like we have to extract the signal multiple times or from multiple persons, and then use some curve fitting techniques to extract the body parameters. Or we can use some machine learning or deep learning techniques to extract these body parameters. Okay, so this is a typical signal chain to process these biomedical signals. Okay. So now I will start with one ECG signals and will describe how many uh, how many types of noises and artifacts are there and how to remove it from the signals. Okay. This is the examples of the artifacts. The basic one is the baseline wandering. So during the recording of these signals, so we are normally taking the breaths. So that respiration is causing the some noise in the signals. It is a very low frequency noise, but it is also a noise. Okay. Next is the EMG interference. So the EMG is also a signal. So, but for ECG signal, it is a noise. Okay. So it is causing due to the contraction of the muscles other than the cardiac muscles. Next is the power line interference, which is typically caused by the capacitive and the inductive couplings. Like if we are using some system to record these signals, okay. So if our system is connected to the power supply, then it can cause that this power line interference. It is typically 50 to 60 hertz, and it is the same frequency as available in our homes in the electricity. And there is some motion artifacts. So it has the frequency range of 1 to 10 hertz. So it is caused by the variation of the change charge distribution at the interface of skin and electrodes. When the electrode is moving near the skin, then it can cause the motion artifacts. If you see in the right hand signal, so there is some baseline is there, some motion artifact which created some peaks, extra peaks than the main signals. So we have to remove these peaks and the noises to process the signal further, or otherwise it can lead to the mislead the diagnosis or treatments. So there are some basic techniques. So basic techniques can remove the simple baseline wonder, these EMG noises, high frequency EMG noises, or we can use some noise filter. But when we are using these filters, we should, our method should be in such a way that it should not remove the information from the signal, main signal, is ECG signal. Okay. So we have to make technique for this particular removal of the motion artifacts. So this is one of the techniques that I have used. Okay. So there are two stages, first stage and second stage. In the first stage, I am removing the low frequency motion artifact, and in the second stage, I am removing the high frequency motion artifact. Okay. So I am considering all type of these four noises and removing using this method. So here in this method I am using a wavelet transform. Okay. So there are various type of wavelet transform: continuous wavelet transform, discrete wavelet transform, and stationary wavelet transform. So what is a wavelet transform? It is a time frequency domain representation of a signal. Like we can represent the signal into time and frequency domains, and using this information we can remove the noises. Okay. So in the first stage, I'm using some pre-processing, using a median filter, using a low pass filter, like removing the very low frequency and high frequency noises. After that, I'm using stationary wavelet transform to decompose the signal into various frequency bands. And then based on that, I am detecting a QRS peaks and then applying a thresholding to remove some particular noise from various bands, and then do the inverse wavelet transform to remove this noise, and then I subtract this part from the main signal, and I will get the low frequency artifact removed ECG signal, and again doing the same process but in different way to remove the high frequency noises. So if you want to know more about this technique, you can go to this paper and check that. So this is the example, like after using this technique. So what is the output? So if you see, the red one is the raw ECG signal, which has some EMG noise in the ECG signal and some power line noise also. Okay. So using this wavelet transform techniques, I am removing these noises. And if you see the blue signal is the output of this technique. Okay. So this is one example. This is another example where some baseline wonder is there, some motion artifacts is there. So I am not disturbing the signal qualities. Okay, but with this I am removing the noise. Okay, so we have to restrain the shape and the signal properties in time domain and frequency domain. Okay, the technique should be in such a way that it should not disturb the signal shape and its properties. Now we have to extract, after denoising the signals, we have to extract the features from the signals. Okay. So this is a typical ECG signal. So we are going to extract some time domain features. Okay. Like these are the peaks, P, Q, R, S, T. So, so this is the R to R interval from one ECG to the another ECG signal. Okay. And these R to R intervals are mostly used for the heart rate calculations. Like if you divide this R to R in like the from 60 divided by this R to R interval is the heart rate of a subject or person. So these are some time domain information of the ECG signal, like PR intervals, QRS interval, ST interval, QT interval, ST segment, and PR segments. So these intervals are very important for the doctor. If you have any problem in the heart, or if you are going to have a heart attack, okay. So there is one example, like doctors knows that when the person is going to be a heart attack, like when the person is going to get a heart attack, this ST segment is changing like 2 to 3 hours before. If doctor will get to know about this ST segment like 2 or 3 hours before, then he can prevent this heart attack. He can give some medication to the patient which can stop that heart attack. Okay, but no one, it is not like if the patient is already in the hospital, then doctor can prevent this heart attack. Otherwise, no one will get to know about this ST segment is changing. Okay, the shape of this ST segment is important for the heart attack patients. Okay, so this is timing information. This is the amplitude information we can extract. We can detect these P peaks, R peaks, T, S, and Q peaks, and use this information for particular disease classification or disease detection. Okay. So if we use this R to R intervals for a long ECG signals, so if we plot this R to R interval, so what is the variation in these R to R intervals? That is called heart rate variability. This is one of the hot topics which are normally used for various type of applications. Heart rate variability. Okay. So using these features of a signal, we can detect disease, we can extract body parameters. Okay. So there are some various applications using the signal feature extraction. So now I am going to tell you about some signal applications where these type of signals and their features can be used. So ECG signal, it is used for the heart rate or the heartbeat rhythms detection. Using the ECG signals, doctor can also tell you about the size and position of the heart chambers also. So if you have any problem in the heart, doctor will first see the ECG signal and then will tell you about what is the problem related to the heart. We can extract the heart rate variability, and we we can also detect some cardiovascular disease such as arrhythmia, arterial fibrillation. There are various diseases related to the heart. Okay, so we can extract or we can detect these diseases using the ECG signals. So PPG signal, the photoplethysmogram signal, this is typically used in the wearable devices, smart watch, smart bands. They are using some light sensors that is extracting the PPG signals from our body and use that PPG signal for the heart rate calculation, blood oxygen saturation level, the SpO2 level, the oxygen, how much is the oxygen available in our blood. Okay, then PPG signals are have various applications nowadays. It is used for the coupleless BP estimation, non-invasive hemoglobin and blood glucose level estimation also. EMG signals. We use the EMG signals for the muscle fatigues to detect the muscle fatigues, identify the neuromuscular disease, disorder of the motor control, and control signal for the prosthetic devices. Like if anyone is a handicap from leg or hand, so we can use their EMG signals and make a prosthetic device, and using the EMG signals he can control that prosthetic hand or leg. Okay, because when our brain processes the signals, it sends the neural signals to the particular body part, and then based on these neural signals we activate our muscles. Okay, so we use this information to control the prosthetic devices. EEG signal, we can use the EEG signal for various applications such as the brain tumor detection, brain or injury, sleep disorder, the depth of anesthesia, coma, diagnose the epilepsy. So these are typical examples of these signals. So there are multiple applications of these signals, and if you combine like ECG plus PPG, ECG plus EMG, then based on the combination of various signals, we can detect or diagnose various diseases. Okay, so there is huge scope to work in these biomedical signals. Okay, so if we don't have the hardware to acquire these signals, then what we can do? So there are some online databases available freely, which we can use for the research purposes of these biomedical signals. Okay, so I'm giving you some few databases example from where you can use these biomedical signals. First is the PhysioNet database. This PhysioNet database typically has the ECG, EEG, PPG, and EMG signals databases. So you can directly go to this link and find the various database and do the your research. There is UCI machine learning repository, which has the 559 data sets, and each data set has the multiple signals of multiple peoples, various age group and sex, gender. So there is third is the Kaggle dataset, which has the 61,308 datasets. Okay, so from that we can, in this dataset, there are few datasets which are related to the biomedical signals, but it has various type of other databases also. And there is Google dataset search also. This particular link, the dataset search.research.google.com. So if you want to search any database, you just go to this link and just type the, like maybe the ECG signal databases. It can give you the various links of the this 1, 2, 3 or the various other databases also. So we can use the information of these datasets for the research purposes or to see how can we use this type of signals for various applications. So what is the opportunities in this biomedical field? If you want to do any research in these biomedical signals, so first thing is to make a hardware for these signals. So we have to make a low power and low noise hardware design, some instrumentation channels, multiple instrumentation channels. Okay, because we already know that these signals are very low amplitude in voice. Okay, so the noise and these signals has the same type of amplitude. So we have to remove these noises from these signals. Okay, then this is the signal noising. You can use various type of techniques. So there is huge scope for the research in this biomedical field. Then after denoising or we already has the denoise signals, then what we can do, we can extract some body parameters, estimation of these body parameters non invasively. Nowadays the hemoglobin and blood glucose are used using these biomedical signals. Like if you know, for the if you want to check the sugar of a person, we have to prick the finger of the person and take the blood samples, and then we can tell about the sugar level of the person. But nowadays, these like one of the example is the PPG signal, which has the information about the our blood sugar, hemoglobins. There is some parameters which we can correlate with these signals, these parameters, body parameters, hemoglobin and glucose level, and use some machine learning techniques to extract these or estimate these parameters. Okay. So these biomedical signals are used for the early disease detection. Like sometimes we don't know about we are going to get any disease or not. But if we are using some wearable device, or if we uh, check our health status in every few months, then we will get to know about if there is any body parameter which are changing frequently, or is there any elevation in some particular body parameters, such as the typical heart rate of the person is 60 to 100. Typical heart rate of a person. Okay, if your heart rate is today, your heart rate is 90, and if you check your heart rate after 1 week, if this should be at a rest condition. So if you check your heartbeat after 1 week, and if it is crossing 1000, like not 1000, 100, okay, so it means your heartbeat is increasing every day. Okay, so then you have to do some exercise, you have to take some medication, you have to take some advice from the doctor how to be how to be stay healthy. Okay, so we can use the early detection and some disease classification, and we need the machine learning techniques to use to do this particular task. Okay, so we can use, doctors are already using these biomedical signals for the diagnosis and treatment purposes. And there are various examples of the human machine interface. Okay, for the prosthetic device, for the wheelchair control, if anyone uh, is doesn't have the leg, then he has to use the wheelchair. So how to control that wheelchair using the biomedical signals? There are various research going on at various levels. So we can use these biomedical signals in this type of applications, and there are other applications also. Like if you want to transmit these signals at the remote location, okay, and if you don't have that bandwidth, like there are huge data. When we record these signals, maybe for 24 hours, for 5 minutes, or maybe 2 hours. Okay, so we have to transmit these signals. So we have to compress the data also. Okay, so there is other application area, like we have to compress the data, transmit the data to the remote location, and then decompress the data and use the original signals. Okay, so these are some references that I have used, or you can also use to get to know more about these biomedical instrumentation and applications. Like first one is the one of the standard and reference book used for this medical instrumentation. Like it also has the information about various type of body signals and the sensors and their instrumentation, like how to make the system. Okay, so next one is like, this is one of my paper that used for the motion artifact removal in the ambulatory ECG signal for the heart rate variability analysis. Okay. The third reference, you can, it is a OPAMP, OPA2333. Okay. This is a Texas Instrument OPAMP. So in this OPAMP, there is some application given by them. Is the hardware, like how to make the ECG acquisition channel that I have shown you in one of the slides. So you can go to this data sheet and you can check how to make a ECG systems like instrumentation channel, buffer, the programmable gain amplifier, and low pass and high pass filters. This is the fourth reference, is a handbook of cuffless blood pressure monitoring. If you get to know more about the cuffless BP monitoring, how to measure the cuffless BP, there are various techniques, there are various body signals which we can use for the cuffless BP monitoring. Okay. The last one is these are the latest books, like 2019 books, the biomedical engineering and its application in healthcare. So you can check these references and proceed. So I would like to acknowledge my PhD supervisor, Professor Mariam Sujai Bagini, and the biomedical group, the embedded system lab in the electrical department of IIT Bombay. And I also would like to acknowledge Assistant Professor Amol S. Deshpande for providing the opportunity to deliver this seminar. Okay. So thank you for your patience. Amol sir?
Thank you, sir.
Yes.
Done with your presentation?
Yeah, done. If anyone, the students want to
Yes. Once you
so
are done, then we can take up some questions.
okay. So if anyone want to know more about these wavelets and how to use these wavelets in the MATLAB, I can show you some demo, just example. Okay.
Yes, sir.
Is my screen visible?
Yes, sir. Yes, sir.
Okay. So there is some.
You can go ahead, sir, as we have
Okay.
some time remaining.
Okay.
So we can go ahead with that.
Okay, I can show you some examples. If you see, like this is a one example of PPG signals. It has some motion artifacts, and it also has the baseline wandering also. So we can use some median filtering or mean average, moving average filter to remove this baseline. This is one example. And then use some specific techniques to remove these motion artifacts. So just like how these signals look like. If you see, this is the example of the wavelet transform. Like when we extract or the information from the signal, so we have to use the wavelet transform. And this wavelet transform decomposes the signal in various frequency band. If you see, like every band has some different frequency. Okay, like consider one example. If the input is of 100 hertz, so the wavelet transform divide the frequency range of 0 to 50 hertz and 50 to 100 hertz. And then based on our interest, the frequency of the interest, we can use that particular frequency band into further to decompose the signals. Like from 0 to 50, we can divide 0 to 25 and 25 to 50. So similar like that, we has the information. Like if you see the left hand side last signal, it is the motion artifact. It is not a signal. So if we make this part 0, then we can remove the motion artifact from these signals. Okay, so I can show you some example of wavelet, how to use a wavelet tool in the MATLAB. Okay, so this, okay. use that wavelet
Sir, can you
analyzer.
increase the font little?
Increase the font. I think this I will try. Just wait. Can I use the magnifier? Okay. Now visible?
Yes,
Yes,
sir.
sir. Thank you.
Yes, sir.
Yeah.
Yes,
Okay.
sir.
Yeah. Okay. Okay. So just so in a MATLAB there is one toolbox called the wavelet analyzer. You can directly write in the command window wavelet analyzer. Then you will get the this wavelet analyzer window. So these are various type of tools like one dimension wavelet transform, two dimension. This wavelet can be used for the image and video. Okay, specialized wavelet transform. Okay, so there is various for the compression. We can use this wavelet transform tool. Okay, so I am giving you one example of 1D wavelet. If I click on this, I will get a one window. Okay, so file, we can load some signals which I have already has the one EC signal. It has .mat format, so it accepts .mat format. So you can save the signal in .mat format and then upload this into the this. So this is a one example. Like it, this is the ECG signal with the huge power line interference noise. Like the when we recorded these signals, we have the system is connected to the power line. So then the noise is embedded into the signal. Okay. So we can use this wavelet tool. So there are various type of wavelet transform. R wavelet, WCHUS wavelet, bioorthogonal, okay, simulate wavelet. So you can analyze various windows and various decomposition level. Okay, 4, 5. Okay, if I consider the 4, if I analyze, if you see here, yeah. So these wavelet transform decompose into the 4 levels: the D1, D2, D3, D4, and the A4. So D is the detailed coefficient and A is the approximation coefficient in the wavelet transform. If you see in the A4, this high frequency noise is removed completely. Okay, this is the analysis. So using this, we see that at every level there is various type of noise. If we denoise, this is portion, the analysis. So here, if I, so this is just thresholding level. We can use various type of threshold to denoise the signal. And if I denoise the signal, just wait. Yeah, if you see in this signal, the red one is the original signal, and this violet one is the denoise signals. Okay, but in this denoising, we did not remove the basic baseline wandering that we can easily use using a high pass filter or some moving median filter. It removes that high frequency noises. So based on our requirements, we can use these wavelet tools. Okay, this is one of the example how to use the signals. Like this is the denoise signals. If you see, okay, only the baseline one is there that can be easily removed by the high pass filter or moving average filter. Okay, you can see the denoise signals. So these tools are available, or you can write a code for particular. Like if I am, we can see the like statics of the signal. There are various analysis tool available, like which type of information it is available, like the histogram or cumulative histogram. So you can easily check if I want to see the approximation coefficients. Show statics. Yeah, that is the same. So this is, you can use this tool for the various applications. Okay, so for the signal extension, image, video, audio. Okay, 1D, 2D compression, and this SWT wavelet, discrete wavelet transform, continuous wavelet transform. So you can, if you want to know more about the wavelet or this DWT, you can just write. Just wait. You can write help and write DWT or SWT for continuous wavelet transform. So you will get to know more about what is this. What is this particular wavelet transform? This discrete wavelet transform. So you will get to know more about how to extract the information using the wavelet transform. It gives some examples. You can go to the documentation of the wavelet transform. So MATLAB and Python can be used for this type of signal processing techniques. Okay. So this was the one example to show you the ECG signal. Yeah, I think. So anybody has any doubts in the PPT?
Yes, sir. You can check the question answer section.
Okay.
Q&A.
Okay.
We have some questions.
Okay. Yeah, Sumitra, thank you. ST segment. Yeah. So I discussed about the ST segment. Like I'm not an expert in this medical field. I am an engineer. So I got this information from two, three doctors. Like when any person is going to get a heart attack, then this ST segment is most important part of the ECG signal, which will reflect that like person will get the heart attack. So if you want to know more about it, you can talk any cardiologist. He can tell you more about this ST segment. Just I know this only information, like when we will get the heart attack, this segment is the most important part that doctor analyze before the heart attack. Okay. Yeah. So Amol sir, you have also asked the one question. Now, how to ensure that meaningful signal do not get removed? Yeah, so it depends on our signal processing techniques, like how we process the signals. So first is the denoising part, in which we can use simple filtering, which does not affect our signals if we are using the particular frequency band which the signal has. Like for ECG signal, it has the frequency band of 0.01 to 150 Hz. If you are using FIR or IR filters, so that filter should have this frequency band. If the band is lower than the 150 Hz, it will disturb the signal. We already know that. We should know the specification of the signals first. Otherwise, we will disturb the morphology of the signal. So that's why we combine some various techniques to remove these noises. How an oximeter will measure the blood oxygen level? Okay, I can tell you more about that. So, yeah. Everybody sees the slides?
Yes, sir.
Yes. Yes.
Okay. So this is a PPG signal. Okay. So when we acquire these PPG signals, we always acquire two wavelengths of these signals, like red wavelength and the infrared wavelengths. Okay, so both will be look like a same in the shape, but both will have the different amplitudes. IR will always have the higher amplitude, because when the blood is flowing in our arteries, and when when the LED lights are passing through our blood, then most of the light is reflected back or scattered due to the red blood cells. Okay, because that red blood cells and this red wavelength has some common frequency bands, like common wavelengths. So if it can reflect, but IR has the high wavelengths, so it can easily pass through that blood samples. Okay, so we will always get the red infrared light as high amplitude and red light as a low amplitude. So ratio of the infrared red wavelength signal by the ratio of the infrared signal, we will get a R value. This is called the ratios of ratio. And using this, there is one equation, S.P.I.T equation. Okay, you can check this book for the equation. So normally the equation is 1110 minus 25R. So using this equation, you can extract the SpO2 information from the PPG signals. Okay, there are some papers you will check. You can check on the internet regarding the how to measure the SpO2 using the PPG signals. Okay.
Okay, sir.
Yeah. Okay. So how to remove the noises from the EEG signals? Okay. So EEG has the various shapes and band. I can see. So when we measure the EEG signal, so we use multiple electrodes. Okay. So every signal has the different frequency band and amplitudes. Okay. So during the recording, ECG and EMG are noises for the EEG signals. First, we have to remove the ECG signals from the EEG signals. Okay, we can use these adaptive techniques or wavelet techniques. Normally, people are used the PCA techniques, principal component analysis techniques, or EMD, empirical mode decomposition techniques, to remove the noises from the EEG signals. Okay, so I think I will include some more references for these EEG signals and PPG signals. Then you will get to know more about these from these references. So when the Amol sir will send you this PPT, I will include more references regarding the EEG and the blood oxygen level. Okay. So what are the different methods of measuring pulse rate, and how to explain the differences in results? Yeah. So most common method is the PPG signal. We extract the heart rate from the PPG signal, pulse rate, that is normally called pulse rate, and ECG signals also we can use. Okay, so these are most frequent methods used for the heart rate calculations, ECG and PPG, and there are other methods also. The impedance method, like in the impedance method, we have to inject current in the body and extract the voltage from that. So that can also used for the heart rate calculations. So these all are the, like, we connect the sensor to our body, and there are some other techniques currently going on, like the camera based heart rate calculations. So you have to sit in front of the camera, and camera will detect the change in the blood volume through your face or through your hand, and then you can extract the heart rate from these signals also, like the completely non-invasive and the non-touching methods.
Thank you. And
Yeah,
nowadays,
yeah.
the pulse oximeter which
Yes.
available in market. So what does that pulse rate measure?
Yeah. So
Which is
that is the PPG signal. They are extracting the our pulse signal using that optical method, using the LED and photodiodes.
But that is not
And
connected with the heartbeat, or it is also heartbeat only.
no, it is used for the heartbeat calculation, that PPG signal, using this variable device.
Because that number I find is very high sometimes compared to.
No, I think some, because there is various reasons for that. If you are using a standard device or or a very accurate device, then you will get the accurate value. One thing, if you are using some local device, it can show you some other values also. Okay, one thing, like
That is
your yeah, there will be fault. Yeah, another is the, if the sensor is not properly placed at your skin now, then you will also get wrong reading. Like if you measure the heart rate during the running, you will get some more values, maybe 120 150 values during the running. If you
that's
are
it.
at rest, yeah, if you are at rest, then your sensor should be connected just above the wrist or arteries.
Okay.
Like, yeah. Okay. Next question is, while there is some difference in the normal range of BP when measured with the digital instruments compared to the analog. What could be the reason? Yeah. So, what do you mean by the analog? That analog is means that doctor is using. That is the analog. And like, is that?
Yes,
Yeah,
sir.
yeah, yeah, yeah. This one, na, upper one and lower one.
Yes, sir. Yes, sir. Yes.
Yeah. So typically, this upper one, doctor always use this device, upper one, not a lower one. Okay, because doctor always believe in the instinct. Like when doctor do it by himself, then he can accurately tell ki what is the upper and lower BP. But in the lower one, there is no doctor. It is the automatic sensor is there, which can detect the what is the upper level and what is the lower level. Okay, but it is almost accurate as this, but there is some error of plus minus 2 or 3 mmHg. Sometimes it can give you 5 or 6 mmHg error. Okay, so typical error is 2 to 3 mmHg. So doctor can also believe in this. Okay, in using this automatic BP device, but typically doctor use the upper one, this analog one, because doctor listen the voice when the artery is opening and blood is flowing through the arteries. Okay.
Okay. Thank you, sir.
Yeah. Yeah, sir. If anyone wants to know about the signals, so I have already given you some references like this FusionNet database. Okay, you can go to this database, and there is one database available that is called MIT B.E.S.T arrhythmia database, which is one of the most famous database are used for the analysis of the arrhythmia or heart rate detection. MIT B.E.S.T arrhythmia database. So all these in the database are free. So you can go to this link and extract the information or signals from this database.
Yes, sir. Actually, what I was
Yeah.
asking is, why, if someone wants to work on image processing, there are some sample images which are by default in MATLAB. So, like that, are there any sample signal files, .mat files
Yeah, I think there is, sir.
in MATLAB?
I have not tried that thing, but there is called ECG. ECG is a command in the ECG. ECG is a command in MATLAB.
Sir, there is one for ECG analysis, QRS
Yes.
detection one only.
Yes. Yeah. I can provide you if you want to do some analysis, I can provide you 1 or 2 sample signals. If anyone want to do something with the signals, I have the signals, or you can easily download from the internet. It is available freely.
Okay, sir.
Yeah.
Thank you,
Yeah.
sir.
Sir, in MATLAB, that MIT B.E.S.T data set is only used.
Yeah, not only, there are multiple data sets are there in that PhysioNet. I have shown you, like if you go to this link, you will get to know more. Like I am showing you now. If we can check this database, are you getting this window? PhysioNet database.
Yes, sir. Yes.
Yeah. So if you see, there are multiple database are there. So I will check the MIT B.E.S.T Archimia database. It is a very old database, like 1975 and 79. So it has the 47 subjects database. So you can go that. Okay. So you can easily download this file. Like it is 73 MB file. Okay. So like if you see, like these are the various database available. You can open these and convert this .dat file into a .mat file or .text file, and then use these signals in MATLAB. So this is freely available. You can download. Okay. And the information about this you will get in the zip file also. Okay. So they provided all the information. What is this database? How they recorded using the 11-bit and 10 millivolt range. Okay. So there is all information are available in the internet. But just you have to go to there and check the information. What do you need from these signals? It's a Velvet Analyzer and app in the MATLAB. No, it is a tool. Like it is not a app. It is a tool developed by the MATLAB, and you can use this for the various type of applications. It is like just to get to know more about like that can be used for your particular application or not. You can easily check, and if it is working, then you can write a specific code for this particular analysis. Our signal is discrete, then how can we apply the CWT on EEG or ECG signals? Apply CWT. Okay. So the CWT can be used for the discrete signal also. You can easily do the experiment in the MATLAB also. There is CWT. If you apply the CWT directly on the, because we don't have any continuous signal in the MATLAB also. If you check, there is some sampling is there also there. Maybe the 1000 sample per second or the 1 million sample per second. But there is always discrete data. There is no continuous data. So we always apply the continuous Fourier transform on this discrete data only. So data is always discrete. You will not get any continuous signal. Continuous signal means infinite data. There is no infinite data. There is always a discrete data. So we always use this discrete data for the continuous wavelet, discrete wavelet, or the other purposes also. Which MATLAB version? So there now I am using 2019 version, MATLAB 2019B. So MATLAB is every year updating. So in every 6 months, MATLAB updates its version, and you can use any version. And there is online free MATLAB also, like online MATLAB you can directly use. Okay. How to measure the hearing signal for detecting the hearing loss. Okay, so here you can use the hearing signals. So now I think speech processing will work for this type of like hearing aids. So the speech signal, we have to process the speech signal and then amplify the signals and process to the person who has some hearing loss. Okay, if you already know like the person has the hearing loss, then you can make an amplifier Okay, so that any signal or any sound coming to that sensor, that it will amplify and process it further for that person that has the hearing loss, I think. Wavelet analyzer is that I type on command window in MATLAB. Yeah, you can easily type wavelet analyzer. Like this is my 2019 version. Okay, so if I type here, just I should clear. Yeah, wavelet that I already used. This is the wavelet analyzer. In that W is small and A is capital. Okay, if you just write wavelet analyzer and just enter, you will get this window, wavelet analyzer. Okay, it is available in, I think, after the 15 or 16th version. Okay, so it is available. So Aisa, you can speak. Aisa, you can speak.
Hello, sir.
Ishan,
Good
please
afternoon.
unmute.
Hello. Yeah.
Yeah, sir. I think mine is 2015 version. That's why 2015B version. That's why I think it's not there. It says undefined function.
So
I
you
think it's
just
after 2016 version, maybe.
It is available in 2018.
yeah,
Okay.
after 18, I think maybe. So you can use after 18 or 17 version. You will
Okay.
get this wavelet. Or you can write, because all these commands are available already, so you can directly write the code, simple discrete wavelet transform. So what is the best thing about MATLAB is, if you write the DWT wavelet transform or MATLAB has the website which can tell you about with example, like what is this command, how to use this particular command. First you have to know what you have to apply. Okay, this is like one example. Okay, how to apply this, like they have uploaded the signal, some signal. Okay, then they apply the DWT. Okay, and they use the simlet 4, or you can use the har, w choose 4, w choose 5, 6, and it will give you the two signals. One is the detailed coefficient, another is the approximate coefficient. And then you can apply some thresholding to do the denoising or compression also, and then do the inverse wavelet transform to get the actual signal, and then plot both of the signals. Like this is one of the example. This blue one is the original signal and red is the reconstructed signal. Okay, so there is various examples you can check on internet. MATLAB, there is no need to go outside the MATLAB. MATLAB is always giving you the examples, multiple examples for particular command, and how to use this command, what is the meaning of this command. Okay, so if you have a MATLAB, you can
Sir,
yes.
in MATLAB, some of the toolbox, they are paid toolbox.
Okay, so yeah, so you can use some crack version of the MATLAB if your university or college is not providing you the MATLAB. You can use the crack version.
Because that higher end toolbox, they need the paid version.
One thing you can do, you can use the Python. Python is freely available for everybody. Okay, every toolbox are free. Just you have to learn the Python, and it is not difficult compared to the MATLAB. The format is different. The algorithms to write an algorithm, if loops, for loops, will work in same way. You can use the Python. I think that is the best thing. If you don't have any paid tool or MATLAB, Python is the most used language for these signal processing techniques or image processing. You can learn Python easily. Is there any more question?
I think we can stop here. If any
Okay.
more questions, then I think they can reach you by email or something.
Yeah, definitely, sir.
So can you provide your email ID in the chat box?
Okay. So I will provide my official email ID, or I will give a Gmail. That will be better.
Yes, please. And can you stop presenting so that I can share the?
Yeah. Okay. Yeah. Definitely, sir. Just I first stop presenting and then we'll write. This is my email ID, deepakberwal@hotmail.com.
Is my screen visible? Can someone?
Yes, sir.
Yes.
Thank you. So I would like to thank Deepak Berwal sir for his very informative session, very basic descriptions in your presentation, and thank you for sticking to the objectives of our FDP. And you have almost covered all the points which we expected. So thank you all. Many of the participants also have acknowledged to your presentation. So please accept a virtual memento from us.
Thank you, sir.
Yes. So would like to be associated in future also. So
yes, sir,
thank you. Thank you very much, sir.
Yeah. Thank you, sir.
Thank you, sir.
Okay, sir.
Aniruddha, sir.
Oh, namaskar, Amol.
Namaskar, sir.
Namaskar, sir. Namaskar.
Okay, so we have just completed the earlier session of the day. So we'll start with your session by 3:30, sir.
Okay, no problem. Perfect.
Is it fine?
Sounds good. Yes, absolutely.
Thank you.
Thank you.
So all the participants can have a short quick break, and our next speaker is ready. So we'll join by 3:30.
Okay, sir.
Amol sir, what about the tea?
Virtual tea.
Virtual tea.
Okay.
I would have been the happiest person to serve you all with the tea and snacks physically.
Yeah. Okay, sir. Yeah. Okay.
Thank you.
It's a balance.
Yes, sir.
Now.
Yeah.
Sir,
Sure. Yeah.
sir के खाते में.